Hey guys, how's it going? It's Dr. Wefer, and to go along with your genetics review that you're doing in your Cliffs book, you're making your flashcards, you're taking practice AP exams in your classroom, you probably notice practically every year there's something to do with operons. What is an operon? Well, let's get into it right now. So before we get into it, transcription and translation, we have to define what is transcription. Well, look right here. Transcription is the process of taking DNA and going to messenger RNA. In a eukaryote, this is in the nucleus, but a prokaryote, this is going to be in the nucleoid region. This is going to be in the midst of translation. Translation is going to be messenger RNA. The amino acids are going to be linked together to form that protein. This occurs at the ribosome. This is the gene control of prokaryotes. This is the mechanism by an organism such as bacteria have a system called an operon. So this whole thing is an operon, and you can think of the operon as the flow of a stream. So this would be considered up the stream. This would be considered down the stream. That's a little bit of the nomenclature of when we talk about the position on a long stretch of DNA. So this actually is DNA. So way downstream, we have the genes that are going to be controlled. This could be one gene. This could be many genes. We're also going to have a region for RNA polymerase to bind to. That's called the promoter. So the promoter is where RNA polymerase, which is the enzyme that makes messenger RNA from the DNA, will bind to the promoter, and it will read the DNA, go down the stream, and when it's able to read over the gene or genes, it will make messenger RNA and therefore eventually make the protein. So the region in between the promoter and the gene or genes is considered the operon. The operon allows this whole thing to operate. This is going to control whether or not this whole operon is going to be turned on or turned off. Now, way upstream, we're going to have a regulatory protein, and this regulatory protein is going to be making a repressor protein. The repressor protein can be active, as seen right here, or it could be broken up in the inactive form. So in one operon, it makes the active repressor, and another operon, it's going to make an inactive repressor. I'll show you guys the difference right now. The first example is the Lac Operon. Lac Operon is when the gene that is going to be controlled is going to be the gene that is going to make the enzyme that is going to digest or utilize lactose. So a bacteria is only going to want to make this gene only if lactose is present. So therefore, this Lac Operon is mostly turned off. It is turned off most of the time. So you could see that this regulatory protein right here is going to be making a repressor protein from this upstream gene that is going to be in the active form. So this active repressor will be permanently, well, not I want to say permanently, it will be bound to the operator in order to block RNA polymerase. RNA polymerase cannot go down the line in order to read the genes that digest lactose. So what happens when lactose is present? So this blue sphere is going to symbolize lactose. An isoform of lactose is called allolactose, and allolactose actually goes into an allosteric site of this repressor protein. So let's watch lactose come in. Here comes lactose, here comes lactose, here comes lactose, and wait for it, boom! What happens is that the repressor protein now is in the inactive form. So now it's going to pop right off the operator, and what does that do? That makes a smooth operator. This allows RNA polymerase to come in, bind to the promoter, start reading the DNA, and it goes downstream, and it is going to transcribe this gene into the protein, into the messenger RNA. Then the messenger RNA will be translated into the protein, and this is going to be the enzymes that are going to utilize lactose. So think about it, people. This will only happen if lactose is present, because why would a cell want to digest lactose if lactose isn't even there to begin with? So this is a case where the operon is induced to make the protein. So the Lac Operon is an example of an operon that is an inducible operon, meaning that when absent, it is off, and it is mostly off. But if it is induced, it can be induced when and if lactose is present, and it will be induced to be turned on. The second example that we're going to go over is the Tryp Operon, and the Tryp Operon is going to be how the bacteria is going to control the production of tryptophan. Now, tryptophan is going to be an amino acid that is going to be essential for the bacteria. If it is not available at all, it's going to need to make it itself. So tryptophan usually is needed to be made. So what's going to happen is this operon is always on. Unlike the Lac Operon that we just saw, which is usually off, this operon is usually on. So what's going to happen is RNA polymerase, you can see right here, it just finished reading the gene to transcribe and translate to make tryptophan. Tryptophan is symbolized by these diamonds. So what happens when too much tryptophan is around? This is an example of negative feedback, where too much of the product will actually turn off the production of the product. You probably have seen this example a few times before. So let's follow the tryptophan. Here comes tryptophan. Come on, tryptophan. Tryptophan, tryptophan, and it goes into the inactive repressor. Normally upstream, it makes an inactive repressor, in which before we saw in the Lac Operon, it makes an active repressor protein. So here, this inactive repressor that is made is going to bond with tryptophan. Tryptophan here is considered a co-repressor, because what happens, it just takes the inactive repressor and activates it. So now the repressor protein is going to do its job. There it goes. Get in there. Get in there, and there it is. What's going to happen is the repressor protein, which is activated by the tryptophan, tryptophan is the co-repressor, now literally represses the production of itself. So what's going to happen is tryptophan disappears, RNA polymerase is going to come in and literally be blocked. And this will be blocked until tryptophan is so low that it needs to make more again. Negative feedback keeps things at a certain level. If it gets too high, it brings it down. If it gets too low, it brings back up. So that's what exactly with the Tryp Operon. So the Tryp Operon, I'm tripping up on the words trip here. So the Tryp Operon is considered a repressible operon, because what happens is normally when the repressor protein is made, it's in the inactive form, okay, and it's usually on, but it can be repressed if and when too much tryptophan is present. Okay, so that's it on the operons, guys. Good luck.